the last thing that might be interesting as regards these two complex comments, like the network surface and the patch, is well, normally the best use for this kind of surfaces is not for creating free-form surfaces like independent surfaces in space. Okay, because each of these two comments has its own problems in that sense. You can see that in this case we have a complexity problem and also some lack of control over the behavior in terms of curvature and interpolation and so on. While in this case there is mostly a topological problem and a precision problem. Okay, but these surfaces become very useful when we have some particular conditions. For example, let's say that I start from an existing double curvature surface, like, I don't know, something like a deformable plane that I soft move in order to create a particular deformation in one area. Eventually, I think I went too far. Yeah, like this. Okay, so we have this double curvature surface, and what I'm going to do, I'm going into the top viewport, take a look at the surface from top, have an idea of where the curvature is, like viewing this in shaded viewport, and I'm going to create a rectangle, like more or less, yeah, this, and move this rectangle in this area and rotate it a little, like this, and place it overlapping this surface, and I'm going to project this rectangle onto this surface. Okay, so now we have this rectangle projected. Well, the actual rectangle is here at the bottom, but this is the projected curve. Okay, and this is creating basically a polyline projected onto the surface of this plane. Okay, which has kinks in these areas because it comes from a discontinuous curve. So if I use this curve to trim the inside part of the original surface, I get this hole. Now this hole is not planar, so I cannot cap it. I need to, for example, if I want to uh, uh, close this hole or cap this hole for this double curvature surface, um, I am forced to use some complex surface tool. Okay. Of course, I cannot use a 4 edges in this case. For example, if I take these 4 surface edges, there is no control over the inner part. There is some interpolation going on, but there is no guarantee about the smoothness of the result. For example, if I reorient this properly, like flipping and swapping the V, reversing the V, which is enough. I see that if I hide all the isocurves for this object, I see some nice and smooth passage of the reflection here, or the light reflection from one surface to another along this edge. But if you take a look, for example, at this, the white reflection here suddenly interrupts with correspondence to this edge. So visually, this is already telling me that there is not enough continuity along this edge. And also along this edge, there is this displacement between this reflection in this area and this reflection here. So this basically tells me that if I conduct some zebra analysis, what I'm getting here is total discontinuity. You see that the black and white stripes don't even align with each other along these two edges. And also here, I might encounter the same problem. You see that they don't align up. And also in this area, they don't line up. So there is absolutely no continuity over the surface of this object, okay? Now, this is always, this must always be considered with relation to the particular workflow that we are into. For example, if this was, I don't know, the surface of a jewel, basically a jewel, when you polish the jewel, you place the surfaces under a brush, rotating brush. And in that case, for example, any discontinuity with this level of detail will suddenly disappear, and you will get to a very perfectly smooth surface as a result. So you will always have to take the 3D model and make some imagination effort to think about what would be the final result of your production process. Okay. But if you want to be extremely precise, so let's say that this is, for example, an aerodynamic surface, and you need to have it perfectly under control. Okay, then in that case, you don't want to use a command that is totally interpolated on the inside. Okay, especially because it doesn't allow taking care of the continuity along the edges. Now, talking about continuity along the edges, there are only few commands that allow to perform this operation automatically. First of them is the sweep to rail. So the sweep to rail, the moment that we use a surface edges as rail and not freeform curve, then if I use this rail and this surface edge and this surface edge are the two rails, and then this edge will be the cross section and this edge will be the final cross section. Okay. Now, if I do this, inside the sweep to rail options, there is edge continuity. Now, edge continuity only refers to the rails A and B, as you can see. What type of continuity do we want for this sweep surface? I want, for example, curvature. Okay. If I do this, the sweep to rail is going to create a surface which has curvature continuity all along these two rails. But there is no guarantee that the same continuity is happening along this edge and this edge. And also, there is no guarantee that the same curvature continuity is happening in the first part of the rails and in the last part of the rails, because it depends on what type of continuity we have between this edge here and this rail here in the connection point. So what happens if I do this with a sweep to rail? Let me flip the Z and reverse B. Okay, and then let's Zebra analyze this. You see that we have curvature continuity here along this edge, and we have curvature continuity on the top edge. So the lines are perfectly coincident and they flow smoothly under specific circumstances. Okay, but here on the left we still see G0, and here on the right as well. Okay, so the sweep to rail is only capable of adjusting the continuity along the rails and not along the cross sections. Okay. In this case, for example, the surface from network or curve becomes useful because this is the only command that allows to select 4 surface edges as outer edges. Okay. And to take into account the edge matching, meaning the continuity along the 4 edges at the same time. So if I specify I want curvature, this is creating a surface which should be curvature continuous all over the boundary. Okay. Now there is the same problem that I was pointing out with the sweep to rail. Because it's not only a matter of what happens along the edges, it's a matter of also what's the relation between one edge with another one. So it's not necessarily guaranteed that we get a precise curvature continuity all over the border. You see that in general, along the edges, there is this kind of continuity. But if we go towards the edges, the corners, eventually in that area, something weird might happen. You see that this dancing around of these stripes is basically telling us that there is some topological problem in this area. But yeah, it's quite a good result we are getting right now, because we are starting from an extremely smooth surface that came from a deformable rectangular plane. Okay, but in general, the problem here is that basically what the command tries to do is, if you select curvature continuity along one edge of the network surface, the surface will be deformed in order to have the first 2 lines of control point properly set and adjusted in order to be continuous with the surface on the other side of the edge. But this is something that can easily be achieved along the edges, but in the end, this surface must touch this corner and must turn around the corner with this orientation that depends on this other edge. So basically, if this other edge is not curvature continuous with, for example, the corresponding extension along the surface cannot be curvature continuous in the corner. So this is the first problem that you get when you try to adjust things with network surface. I can show you this with another example in order to exaggerate a little, but this will make things a little more clear. So if I take this plane and copy it, copy it so that this vertex corresponds to this one, and then copy these two so that this vertex corresponds to this one. Okay, now I want to create a surface here which has the curvature continuity with all the four edges. But what I'm going to do, I'm going to take this surface here and activate the control point and orient this edge like this. Okay, just like this. And then I choose the network surface, edge, 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 and I want curvature continuity, okay, along the edges. And I get this result. Now you see that in this case, for example, my surface must be curvature continuous along this edge with this surface here, but also curvature continuous with this surface along this edge. Now this is impossible in this area, because curvature continuity with this surface keeps the original surface flat in the first area. But when we get to this corner, in order to be curvature continuous with this, the surface cannot be flat in this area. And therefore, we lose the curvature continuity in this corner. Okay? So in general, the network surface is capable of considering the level of continuity along the whole border of the surface, but it depends on the original set of edges that we are using. Okay, so it's not that you automatically get to a constant curvature continuity. In our case, things are particularly regular because we started from a double curvature surface in an internal part which was trimmed, but all the orientations that we get along the edges of this hole are always curvature continuous, okay, because they belong to an internal part of a surface. So this that we are doing here is using a network surface to patch this surface, okay? One thing that we can do instead of creating this, this complex topology right now, which is a network surface, we can use the patch command, because the patch command in this case has some particular feature that makes it suitable for this kind of situation. So if I patch using this surface edge, this one, and this one, and I preview, you see that I start getting this kind of result, which is already quite smooth, because we have automatic trim, which is actually trimming the patch surface. If I don't do this, I can see that the real surface is coming out like this. But I don't need the outer part, so I can simply trim it directly, okay, and eliminate the surroundings. As regards the inner part, there is one particular feature that is called adjust tangency. So if I have used surface edges as input line, the patch is capable of considering the orientation along the edges of the adjacent surface. But it just adjusts tangency, not curvature continuity. Okay, so there is some continuity taken into account, but it's not as profound as curvature continuity. Okay. If the surface that we are patching is smooth enough, we can also work with the stiffness, make this surface a little more elastic in order to better adapt to the outline. Okay. We can also increase the number of spans. There is a limit. I don't remember how many spans you can create, but normally Rhino starts to have problem when you create tens of thousands of control points, which means that you can increase up to thousands of spans. Now, in this moment, we have 400 spans, more or less. So if I select, for example, 50 by 50, we should have a huge amount of spans, but Rhino still can handle this kind of complexity, okay? But normally, you don't want to work with this kind of resolution for your topology. But then there is another feature which is more important than this. We are patching a surface which has its own topology, right? So the patch says, okay, do you want to select a starting surface? So is this patch basically patching an existing surface that you want to respect in terms of topology? In that case, select starting surface tells the patch that you want to use the surface topology. You see? So we are basically patching a surface using the best possible topology for this particular situation. Okay? So you see that the patch suddenly becomes quite useful because it allows to create a less complex topology. Like in this case, if I, for example, say, okay, I want, I deleted the input, sorry, my bad. Let me repeat. Because now when I select the starting surface, the starting surface itself becomes an input for the command. So I don't want to delete the input. Okay. So, okay, I get this patch surface. And if I activate a control point, look at what we got here. This is exactly, or well, not exactly, but it's the topology of the patch that corresponds exactly to the extension of the surface that we selected as starting surface. So we see that basically, if I select also this one here and activate its control point, you see that there is a whole part of the surface which has the same identical topology, but you also see that there is some deviation between the topology of the actual patch and the original surface. So this patch is not rebuilding the original surface, it's a patch, okay? It's a different thing. And as we work with a patch, the patch is never precise 100%, okay? Especially if we work with a, let's say, permissive topology like this one, okay, which has very few spans. So it's impossible for this patch to adapt precisely to the edges, okay? If I don't use a select start surface, for example, if I lock this, for example, and repeat the patch using this surface edge, surface edge, surface edge, and surface edge, don't select the starting surface and use this kind of patch with this amount of spans and its own topology, okay? Then I get a surface which is basically more precise because it has a more complex topology that is capable of adapting to the existing one, okay? But even in this case, for example, this is the patch surface, and this is the patch surface with let's say, topology adapted to the surrounding surface, okay? If I consider these objects here, I might also make some curvature consideration. I'm not going to use the zebra analysis right now because it's less precise. I want a more precise analysis. So I go here and perform some curvature analysis, just the range of this, and also adjust the mesh in order to have a more detailed representation. Well, it also more detailed than this. So I go into detail control, refine this mesh, maximum aspect ratio, regularize the aspect ratio, and also, well, increase the initial density. So we start to have more polygons here, and also I will use a maximum distance edge to surface of 0.25. Let's say this is going to, it should actually increase the amount of polygons, especially in this area. It's not doing because eventually this is still too much. Let's see if we can maximum edge length of 0.25. Let's see if this creates a more dense mesh. I think so. Yeah, perfect. So it's something that it's barely possible to handle from Rhino, but this is enough to see that we don't have a perfect curvature alignment between these two surfaces. Okay, so this is what I wanted to achieve. Also, what I'm going to do, I'm going to remove this object from the analysis, which was the patch with the perfect topology, let's say so. And I'm going to go back to the first patch that we have created. I'm going to move it from this end to this end. And I'm going to add this to my analysis. You see that also in this case, there is no curvature correspondence. So let's remove this, move it away, take the this was the network, and add this to the objects. And in this case, you see that the network is capable of considering the curvature continuity along the border, okay, which was our condition. But anyway, you see that this is always a patch surface, okay? So the behavior in the inner part is always the result of an interpolation. So it has nothing to do with the original curvature of the surface, which should not have this kind of noise in this area. It should only have some gradient like this one on the on this part, okay? So no matter how you rebuild this hole here, you are always going to get some weird behavior. Now, if this is you want this to be a perfectly smooth aerodynamic surface, you should also take into account that even the curvature control along the edges is producing some kind of sudden curvature variation, which is the jerk that we were discussing yesterday. Okay, in that case, from an aerodynamical point of view, this surface with this patch should not be exactly the perfect result. Okay. Okay, so you see that also continuity problem becomes quite relevant when you work with these complex comments, and it's very difficult to obtain perfect continuity. That's why, for example, in my book, I played around with a method which was basically starting with a deformable plane and building the whole surface of a car, which, by the way, was this one. This was exactly the final result. Okay, so this is one single deformable plane that I edited with control point in order to create all these details and deformations along the surface of the car. Once I had the final shape, I just trimmed the surface with a trim line. Okay, so this makes this part of the surface perfectly continuous with this part because they are part of the same surface. Okay, so that's why this method probably is the safest method to obtain a perfectly smooth and aerodynamic surface. But it takes, well, sometimes a lot of control of the topology in order to get to this type of final result. Okay, the normal processing, for example, automotive design is designing the parts independently from each other and taking into account the continuity in the connection line by hand, or of course with the help of a software, but one by one. Okay, so that's the normal approach. But you can also play around with this other method and see if you manage to obtain more continuous results. So there was some questions about the patch command, Tiziano.
It was a bit more general. I mean, thinking about all the methods, all the methods we were looking at in relation with some curves that are not planar. If you could, I mean, basically you have to know what is the scope of it, but what would be the best solution? Because if we recap, we saw the patch that have some good thing and some less good thing, let's say, and then there is the surface from different curve.
From network of curves, yes.
Exactly, networks. Are these two the only methods? Because otherwise we use planar curves and then we manipulate it as we were doing.
Well, actually, it depends. It depends on what you need to do. For example, if you need to patch this with a surface, there are also more complex methods. It depends on what you want to do. For example, if you want to achieve, let's say, the best possible result, I don't know what this means in general because it depends always on the particular case, but you eventually
I'm referring to have a good topology that is well editable. Like in the beginning, we were seeing different.
Yeah, exactly. That's what I was going to show you in this situation. For example, one complex method or one method that would allow a better control, for example, would be to do something like this. I have this surface. and I want to patch it the best possible way. One thing that we could do, for example, is take into account the idea of creating inner sections. Okay. So, for example, let's say I want to create not only patch the surface, but also create some kind of surface variation in the inner part. Okay. In that case, I need the right topology, of course. So what I can do, for example, is something like this. I can create a section. I'm going to create a section of this surface from this point to this point. Of course, I can be more precise, okay, in order to obtain these two lines here, okay? I can be more precise. If I want to align with the midpoint of this edge and this edge, I can do it. I mean, there is no problem, but I just need to simplify the process, okay? So we have these two lines belonging to the surface. So if I want the inner surface to be curvature continuous, for example, with the outer surface, I can also create an interior edge here, which is curvature continuous with this line and this line. This would serve as an internal guide for my surface, okay? So if I do this, well, how can I do this, first of all, okay? So I can create a first example of guide curve by using, for example, the blend curve, the adjustable blend curve. And of course, I'm going to blend this line here with this line here. I cannot use curvature continuity because else I'm going to get a degree 5 curve. So I need to use a tangency, okay? Which means curvature discontinuity. You see this jump here in the graph, okay? But it doesn't matter for now. I just need this curve. Once I have this curve, if I need my surface, which is going to use this curve, to be curvature continuous here and here, I need the surface to be based on a topology that not only has 2 control points and 2 control points, we need 3 control points here and 3 control points in the end part. So I go along this curve here and eventually start to add knots to this curve, like for example, 1 knot here and 1 knot here. Okay, so now we have a degree 3 curve with 3 control points. We know that this is still tangent because the inserting the knot doesn't change the shape of the curve. So this second control point went closer to the edge and to the end point, but is still aligned with the tangent direction, as well as this one. Okay, so we just added these 2 control points that are useful for determining the curvature continuity along these edges. And if I want, I also can add other knots, for example, 1 here, 1 here, and 1 here, okay? Other 3 knots, which means other 3 control points. So you have 3 for initial curvature, 3 for final curvature, and 3 that this curve is a degree 3 curve. These points obey to the rules that we saw for degree 3 curves in terms of topological editing. So for example, I can take these 3 points, set the z value to a value like, for example, this point here. So I am telling this curve to reach this particular height, okay? And I can create this kind of controlled deformation for this curve that will correspond to eventually the surface that will use this curve as an internal guide, okay? So everything is set right now, and I can use, for example, a network surface, like using this edge, this curve, and this edge, and then this edge and this edge. As we are inside of a surface, which basically the 4 outer edges are part of one single double curvature surface, then this has enough continuity to respect the curvature continuity that we are setting along the whole border, okay? And moreover, we are tending the software that we want to pass through this interior edge. Now, this interior edge has the right amount of control points, but we didn't take into account the position of the third control point. So there is some deviation between the surface and the actual cross section. If we want to be more precise in this case, what we must do is take this curve here and take this curve here, and well, where is it? Uh, you match it. Okay, so I'm going to match this line to this one, and I want curvature continuity. And you see that there is some deformation going on here. The tangent control point eventually is not going to move, but the curvature control point, yes. Okay, and I can preserve curvature continuity on the other end, but actually there is no curvature continuity, so it's not preserving anything. But no matter, I just want to take into account this direct continuity here, and then I will do the same like with this and this. So here we get some deformation, as you can see, and hit OK. So we didn't change the topology. We simply changed the position of these control points and this one, so that our cross section is actually curvature continuous along this edge with the correspondent part of the surface that's relevant, which is this and this curve. Okay, so now my network surface is going to be even more precise, because the internal guide is telling basically the same thing than all the rest of the edges that are involved. Okay, so basically you can build your network as you want in this case, because you are starting from an existing surface which is guiding the behavior of our network surface. Okay, there is no possibility, for example, in this case, for this orange surface to do something weird in between, because I am using the less amount of control of interior edges possible. Also, if I, for example, do the same thing in the other direction, like sectioning these from like here to here, and blend curve from here to here, tangency, it's okay. And then add some knots to this, like for example, one here, and then another one, and then another one. And then eventually, let me see. Yeah, I need another couple of knots, like here and here. So we have 3, and then 3 in the inside and 3 on the other hand. And I can take these 3 points, and I must bring them, as we already observed, to be coincident with this center point here. So I would simply move this point here. Sorry, this I need to show the control point. Yeah, okay, or else they are going to disappear. Okay, so I'm going to take this control point and move them so that this point is coincident with this point here. These 3 points are not necessarily aligned. I mean, this, and this. So I have to double check that things are eventually working properly. You see that if these 3 points are not aligned like this, the 2 curves will not intersect here. You see that it's a very small deviation, but this eventually could affect the result. Now, I can also ignore this situation, because we know that if I execute the network surface once again, like curve, 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 and curve, 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 we also know that the surface from curve networks uses the interior curves with this tolerance. So if the deviation between the 2 curves in the intersection point is more or less this value, there is no need to adjust precisely that intersection. Okay, so this is the method that you might want to use. But if you do this, remember that as we are not using just one interpolation, but we're using 2 interpolation in 2 different directions. In this case, the network surface could have some curvature problem. So let's double check. 1, 2, 3, 1, 2, 3. 1, 2. Yeah, you see that, for example, these parts here are basically creating some undesired counter curvature here towards the bottom. And this is something that when it starts to happen, there is no way to recover it with a surface from curve network. Eventually, what you might want to do in this case is patch using all these lines and creating a patch surface that is only considering tangency. Okay, so this is the limitation that you have. Once you have a surface like this, there is basically very few things that you can do in terms of topological control. There is no way, for example, of realigning the the topology of this patch in a more interesting way with regards to the surrounding surface, what you can do eventually, the only thing that you can do is that as you have this patch, which is getting to this outside perimeter here, you might want to shrink this trimmed surface in order to reduce the topology and eventually have the less amount of topology which is needed to represent this kind of surface. Okay, so if I try to shrink this and I activate the control points, you see that I have a smaller set of control points. But this is not affecting the orientation of the topology, and it's not affecting, for example, the fact that the surface is not in contact with its edges. So it is still a trimmed surface. Okay. So in this case, this is the best thing that you can do with a patch. So you have tangency here and a trimmed surface, but it's still a trimmed surface. So you always have to find the balance between the control that you need in terms of geometry and geometric relation, so continuity, and also the topology, the perfect topology. So for example, probably in this case, there is also a very particular situation where the cut is not aligned with the original surface topology. So this is also creating some problems in terms of topology, because probably the best thing, if, for example, we create a simpler situation, okay? So I'm going to take this surface and I'm going to create some isocurves, like, for example, here, here, and then toggle, and here, and here, okay? And I'm going to trim this surface here. Now, this is a topological trim, okay? This is a geometric trim. So topological trim happens in the UMB direction, the parametric direction, okay? If you have this, things are way easier than in this case. Because if you use, for example, some network surface, in this case, the network surface is oriented and is aligned exactly like the underlying topology. Okay? So if a network surface using this surface edge, surface edge, surface edge, and surface edge, the topology that we get is already aligned with the original one, you see? So the isocurves flow exactly in the same direction as the underlying isocurve. If I try, for example, to, let me hide all the rest. Okay, if I try to patch this, remember that as the patch is not based directly on the input geometry, the patch still creates its own topology, as you can see. So the patch is problematic mostly for this reason here, okay? So there is no way of adjusting the topology of the patch to the surrounding topology. On the other hand, if this is a topological cut that we perform here, there is also another possibility that we have. Any cross section that we create is an isocurve. So if I start to create, for example, isocurves flowing from one edge to the opposite one, they will represent exactly the edges, the actual isocurve of the original surface. And so if I use them in order to create a network surface, saying I want curvature continuity, that curvature continuity is going to be absolutely perfect. And I can do this, for example, with the simplest command, possible command, which is the sweep to rail. Because if I sweep to rail right now, with one rail being topologically connected to the underlying surface, and the other one as well, and I take as cross section, I am taking actually an isocurve of the surface and another isocurve of the surface. So it means that this curve here is exactly curvature continuous with the rest of the surface in both ends, because it is an isocurve, okay? And because this is a degree 3 surface, so it has an internal curvature continuity all over the surface. So if I do this, I just need to have curvature continuity along the two rails, okay? And I don't need to change anything about the cross section because they are already curvature continuous, okay? And so I get this patch here, patch in general, okay, inside the surface, which is almost perfect. And moreover, I am getting to this object here, which is not a trimmed surface. It is in contact with its edges, okay? And so I can alter the internal part of the topology, not these control point lines here, but I can add control points, for example, in the inner part if I want to create, I don't know, bulges or engravings or whatever. Okay, and this will maintain this aerodynamic flow of the patch with respect to the original surface. But this is only if you have a topological cut and not a geometric cut. The geometric cut cannot be aligned with the underlying topology unless you use a patch with a starting surface. But you saw already that the patch with starting surface has always some curvature discontinuity problems. Well, not discontinuity, but variation problem in the inside and curvature discontinuity along the edges. So it's not the best thing. So you always have to find the balance between the workflow that you want to adopt to perform this kind of operation. Okay. Also consider one thing, which is, well, I would say that it's quite important if you want to play around with aerodynamic surfaces, is this one. We saw that, for example, the sweep 2 as well as the surface from network of curves are capable of creating a surface which is which has some geometric continuity with the rails as regards the sweep 2 rails and the 4 edges as regards the network surface. Okay, but we must also take into account one particular situation. So I'm going to take the usual, well, I deleted them, but anyway, I'm going to take the usual deformable plane like this, and I'm going to...
What is the command to find the deformable plane?
It's this one, rectangular
yes.
plane corner to corner, and you select the deformable here. Or if you want, you can create a button yourself, which is this is something I did.
All right, because I was like struggling where it was this icon.
Sorry. I didn't think about it. Sorry, guys, but this is a custom button. If I shift right click, you see this is the command, which is in RhinoScript is exclamation mark and then underscore plane underscore deformable. And the icon, I did it myself. Okay, is the original icon, but with an additional set of control points and on the inside and on the half the 4 edges, the midpoint of the 4 edges. So this is totally custom command. And so I'm going to copy this. Sorry, I'm going to copy this here. Okay, and I'm going to create some deformation here, and yeah, with a soft move actually. So I'm going to select only this point here. So I'm going to deform this area, and I'm going to deform also these points here and deform them like this. Okay, so we have two double curvature surfaces facing each other, and what I want to do, I want to create a smooth connection with curvature continuity between these two things here. Now, of course, the best thing that we can do right now is eventually create a blend surface. So if I blend this with this, I can automatically set the continuity with curvature, right? But the problem is, remember that if you set curvature, you will have a single span cross section coming up from this thing. So you will have a 5 degree 5 surface in the B direction, okay? And we don't want this, okay? So the best thing that we can do here, if we want a degree 3, is build at least one cross section, okay? So what happens if I, for example, take a blend curve, which I can do in this case, and blend this edge with this edge here, only with tangency. So I get a degree 3 connection line, okay? If I have this, I have this topology for the cross section. And the sweep to rail can adjust continuity up to whatever, because basically we see here that we can increase to curvature. But take a look at this. If I set position, then this thing comes out with geometric continuity G0 along A and B. So there is only contact between the 3 surfaces, but some creases are coming out, okay? If I set this to tangency position, then along A, I have tangency, but along B, I still have creases. If I set tangency, tangency, I start to have tangency continuity along both rails. But if I switch to curvature in A, B automatically switched back to position because our cross-section only has 4 control points. And the command needs to use 3 for curvature, and only 1 is free for B continuity. So if B continuity can be set only by 1 control point, the only possible thing is position continuity, right? So the sweep needs to have the right topology in order to perform the desired continuity operation, okay? So in this case, for example, we can do 2 things. First one, rebuild the cross-section using 6 control points. Now the problem with this, and if I do this, I can also increase to curvature, curvature, of course, right? But the problem with this is that if I rebuild the cross-section, I have a different behavior of the curve, okay? Different shape. Now, take a look at this, okay? I'm going to rebuild this line outside from the sweep to rail command, okay? With 6 control points instead of 4. You see that the actual shape that the curve is taking is perfectly or almost perfectly identical to the original one, because there is a maximum deviation happening here of 0.009, right? So it's a very, very small deviation, and it is not being deformed like it was deformed inside the sweep. Why? Because the sweep not only was rebuilding the curve, it was already adapting the cross-section to be curvature continuous with the 2 opposite edges, okay? So if I rebuild this outside from the sweep to rail, I am creating the right topology, but not the right continuity, because I still have tangency and tangency, okay? Because I have basically almost didn't touch the geometric aspect because the maximum deviation was very small, okay? But I don't place these 2 points here in order for this curve to be curvature continuous with these opposite edges. So if I go into the sweep to rail and use this cross section, which has the right topology to create a curvature curvature, you see that curvature curvature is acceptable even if I don't change the cross section. But in order to have this kind of continuity, the command is changing the shape of the cross section, okay? So this is a particular case in which it's evident that if we don't have the proper, not only topology, but also continuity condition for the cross section, the surface cannot be created with that kind of continuity if we want to maintain exactly the same shape for the cross section. And this is happening here, which is something quite visible because we are on one of the endpoint of the rail, but also happens if you have intermediate cross sections, okay? So if you make the effort of creating a sweep, of pushing this button, going inside this window, changing continuity level to this, Rhino assumes that this is very important to you, more than the shape of the cross section, okay? And therefore, it prefers to change the shape of this cross section instead of creating some continuity problems in these points here. The other thing that you can do eventually in this case is use the proper topology, like 6 control point degree 3, but at the same time rebuild the cross section with, I don't know, more control points. Now, if you do this, you are saying basically that your cross section has become more and more complex, okay? Yet this cross section, which in this case adheres to the original shape, is not curvature continuous with this surface, not even with this surface, okay? So in this case, what happens is that your 3 control points that are used for curvature continuity are very close to the 2 rails, okay? So if I do this, I say, okay, I can also set curvature curvature, right? Because I have 32 control points. And this rebuild is way more precise than the original rebuild that was happening with only 6 control points, because rebuild redistributes the control points along the path in something like having a uniform knot span. And so the control points are more or less evenly distributed. So creating a curvature condition means that the 3rd control point is way far from the rail. But if I have 32 control points, the first three lines of control point are very close to the A and B rails, okay? And if I determine that I want curvature continuity, this curvature continuity is set locally. And so, yes, in this moment, I have curvature continuity along these edges, especially in this part here and this part here. But you see that it is resolved locally. So this is something that you don't want to get as a result. Because if you take a curvature analysis of this thing here, you will have this kind of weird behavior. Well, curvature is still continuous, but the variation happens in a very, very limited span of surface. And so you have this kind of jerk, actually, also eventually some pop or crack, because curvature changes very, very fast, okay? And so this is not an aerodynamic surface, of course, okay? Moreover, you start to get some, to have some problems in this connection part, especially because you can see that the surface is continuous, but you are not respecting the curve, which was this one. Because the first three control points of the 32 control points curve that you have rebuilt inside the common are being displaced in order to have curvature continuity. So the displaced or the rebuilt cross section does not correspond to the cross section that you were using, okay? So you see that you have many problems in this case with this sweep to rail. Okay, even if you eventually could have the idea of controlling the curvature continuity along the rails, it's very difficult in this case that you can get to a precise result. So once again, how can you regularize this situation? Well, it depends on what you want to get, but as we have performed a dynamic rebuild inside the sweep, this is still the original curve, okay? So in this case, for example, if I want to create some nice double curvature connection surface with curvature continuity, eventually I prefer to take this, which is a 6 control point degree 3 curve, and match it before creating the sweep to rail. So if I match this with this, I want to have curvature continuity on one end, and I match this with this and have curvature continuity on the other hand, like this. So you see that this third control point and third control point are already in a configuration that guarantees curvature continuity between this edge, this line and this edge, and this line and the opposite edge. So now if I sweep to rail, this with this, my cross section not only has the right topology, it also has the right continuity. Now, you see that in this case, you see that do not change cross section. I simply need position continuity because I already have the rail and the cross section in the right configuration. And even if this guarantees the continuity only inside, only with correspondences to this vertex here, okay, I prefer this to this. Why does this happen? Why the command is still deforming this cross section if it is already continuous and has the right topology? Because the sweep to rails must take into account curvature continuity all along rail A and rail B. So it's not like, oh, okay, the cross section is continuous with A in this point and with B in this point. Well, then let's sweep it. No, because in order to maintain curvature continuity also in this area, this cross section must become more curved like this. And therefore, there cannot be a sudden variation of the cross section because it is a continuous smoothing, continuous sweeping, then this first section is adapted, okay? So I don't want this. I don't want to lose this cross section. So what I do is, as this curve here is already in the proper continuity conditions, I prefer to keep these two positions, okay? So I simply make this cross section sweep. This means that I don't have curvature continuity along the rails, only in this point here, okay? So once I have this, I have a surface which is not curvature continuous. If you take a curvature analysis, it's evident, okay? You have these jumps in the color, but we have a surface with the right topology. 6 control points in the cross direction with degree 3. So what I can do is eventually go into the surface utilities here and eventually match, sorry, not merge, but match surface, like matching this surface edge here with this surface edge in order to have curvature continuity, and I match this surface edge with this surface edge in order to have curvature continuity. You see that if I do this, I go back exactly to the same situation that I had with my sweep to rail. Okay, so you see that basically what this thing is telling you is that this curvature condition for this edge is not compatible with the continuity condition along this rail. This is something that eventually I can show you. The reason why I can show you this with a blend surface. Okay, so let's say I want to blend surface this edge with this opposite edge. Okay, and I set this without interior shapes just to simplify things a little. I want curvature, curvature. Okay, so now see that this surface here that is coming out is curvature continuous, but also this one is curvature continuous. And also, this is curvature continuous. So curvature continuity is not something that you solve along the rails only in the end point. It affects the whole rails, okay? So what we are doing here is creating a new connection surface with curvature continuity, exactly like the first one, but with a totally different shape, even if we are maintaining the same level of continuity, okay? So it's for this reason, is because the sweep to rail has to work all along the rails, that you cannot rely simply on the topology of the cross sections, okay? So in this case, for example, if you want to adjust things like the best way you can, eventually you could use a network surface, but we still miss the fourth sides in this case. So I would blend this edge with this edge. Tangency, tangency is enough. If you want, you can change the topology in order to have better continuity, but I left these sides almost flat, so there is basically almost no difference, okay? And therefore, I can use a network of curves. So this and this, and this, and this. Now, A and C are surface edges. So I can set this to curvature, curvature. While B and D are free curves. So there is no possible continuity but the position. You cannot select tangency and curvature, okay? So if I hit OK, I am creating a surface which is curvature continuous along this edge and this edge, okay? So if I take these three things here and perform a curvature analysis, you see that now I start to have a more interesting flow of the curvature around here, but well, a little worse in this area. And I suppose that this depends on the fact that this edge here, this curve that we have created, is not the right continuity along this edge here. But you see that here, things are working perfectly fine because this curve is curvature continuous with the adjacent surface. So in this case, we are considering all the surface edges and cross sections as basically, they all have the same importance. Moreover, the command allows to select curve continuity, geometric continuity along the surface edges. So this eventually would be the best solution in this case. Of course, you have to adjust the continuity between this curve and the adjacent surfaces, not taking tangency, tangency, like we did here. Okay, we adjusted to curvature, curvature. Okay, so you see that it's a complex set of consideration when you create this kind of surfaces. It's not just what's the best process. It depends. It depends on what you want to achieve, what's the importance of the input curve that you are using, how important is to have a smoother aspect or a complex topology. It depends on many considerations, Tiziano. It's not a one single answer for all. Well, okay, so if you don't have any further questions on this, okay, if you don't have any further questions on this, I would analyze the last, let's say, topological situation, which has some relevant meaning in any workflow, which is basically how to draw over complex surfaces, how to draw details over complex surfaces, okay? So, for example, let's start with something very, very simple. Something like, let's see, well, something like this. Okay, a oh, and in order to do this, I must get rid of all the actual geometry. Yeah, so let's say that I do prefer to start from a clean situation here. So I'm going to create a deformable plane. Tiziano, this is a custom command. So deformable plane, and I'm going to activate the control points and make some deformation to this. Okay. So the first deformation that I'm going to create here is very, very simple. I'm not going to use the soft move in this case. I don't need it. What I'm going to do, I'm going to create a control deformation like this one. For example, I'm going to take, well, if I asked you, what's the size of this rectangle? Well, we all agree that it's simply this size by this size, right? So let's say 37 by 24, okay? But we know that if I select this surface here and go into details, there is another information, which is this one, the domain, okay? Now you see that in this case, the domain is coincident. Well, not that much. I don't have many custom commands. Well, probably I only have the deformable plane. But anyway, you see that in this case, for example, the domain, the U domain and B domain are exactly identical to the actual geometric size of our plane. This is why, this is because the rectangular plane, if you draw a rectangular plane, the rectangular plane is a bilinear surface. It's linear in one direction and linear in the other direction. It means the topology of this only has one control point and one control point at the start and end of each side. So it's a bilinear topology. So there is constant speed from one end to the opposite end. And so the domain is coincident with the geometric aspect of the surface, okay? But what I'm going to do right now is this. So I'm going to take this surface, and I'm going to take, for example, this set of points here, and I'm going to scale it down and move it here. And now, what's the size of this geometry? Because geometrically speaking, the size of this geometry is basically 24 on the right, and if you want to be like to give an approximate dimension, it's 19 on the other hand, and it's 37 at the bottom, but it's, let's see how much, 29 on the top. Okay, but if we take this surface and go into details, the details always says, oh, 37 by 24. Now, this is something that we should already understand. If we created the surface with this topology, the domain is actually the variation of the parameter t from one end to the other end. If we alter the topology, if we change the position of control point, we are not changing the extension of the domain of the surface. So the parameter t always flows from 0 to 37.18 and something in order to go from left to right. So taking into account this isocurve here, this point here has parameter t0, u0, sorry, and v is always the parameter v that corresponds to this isocurve along this 24.32 range, okay? So it's just that we are compressing the domain, but we are maintaining its range, okay? So what does this mean? This means that in the area where control points are closer, the surface is lower, okay? And in this area, the surface is faster. But nevertheless, the domain is always constant, okay? So the domain has nothing to do with the geometric aspect of a surface, with the geometric dimension of the surface. And this is the reason why, if I, for example, don't consider the actual visible knot lines, and take, for example, an extract isocurve command for this surface, you see that this surface is basically, the left side is moving slower in this area, and then it becomes to move at the same velocity, okay? Therefore, you have this deformation. And as well as if you toggle the direction, you will have this deformation occurring because this area is slower than this area here at the bottom, okay? Now, what are the consequences of this situation here? Well, there are some comments. For example, if I want to take the surface and not only change the velocity and keep the surface planar, okay, I want to also take this area here and move it up, like creating this kind of thing. I will only maintain the original domain dimensions, okay? So I have this situation here, and what I want to do, I want to draw on this surface. Now, the first command that allows to do this is actually the interpolate curve on surface. We already saw this. It allows creating curves which lie perfectly, well, perfectly using the absolute tolerance on the surface that we have selected. Okay, so very complex curves with lots of control points, uneven distribution of control points, very complex topology. Okay. And there are some problems. For example, if I want to create a curve with vertices using this technique, I cannot do this with one single execution because the points are always smooth points, okay? Because this is an interpolated curve, right? So I cannot create vertices. In order to create vertices, I need to create, for example, one interpolated curve and then execute another time the same command. I start from the endpoint. In that case, I can create a vertex because they are two different curves, and then a third one like this, and eventually a fourth one in order to connect these. And I'm creating a interpolated curve on surface with vertices that I can join later together. Okay, and I can use it to do whatever I want. So this is the quickest way of drawing on over a surface, but it's very difficult to control the result because the interpolation depends not only on the points that you are clicking, but also on the shape of the underlying surface, which makes the curve, the interpolation, dance around more than it would be dancing around with a standard execution of an interpolated curve like this. Everything is moving here. Now, in this case, the movement is determined by the points and the surface. So it's very difficult to control it. So like, for example, drawing I don't know, a text on this surface is actually very, very complex if you try to do this with an interpolated surface, okay? So how can we do this? In this case, what we have as a possibility are, first of all, projections. But projections always produce some kind of a strange result because if I create, for example, a text object like Rhino, okay, as curves, and I'm going to group the curves in order to don't struggle when I want to select them, and eventually give this a height of 5 millimeters. Okay, so I get this right in here, and I move this here on top of the surface. Now, of course, I can project this onto the surface, but if I do this, depending on what projection I use, in this case is the vertical projection. So you see that the writing is being completely distorted by this projection, okay? Because it encounters the surface at different level, at different height, in different positions. So there is this stretching and deforming without control, okay? So projection are normally not an option unless you do a very particular process in which you set the projection direction normal to the surface. So in that case, the deformation is the less deformation possible, but I'm not going to discuss this because it's a very, very specific situation. What I prefer to discuss here is a more complex situation where I want to place a controlled shape where control shape, probably the best example is a text, which has a very particular shape and also very particular proportions, okay, over a surface with some topological complexity and also geometrical complexity. So what I'm going to do right now, I'm going to the front viewport, and I'm going to use some freeform curves. So I'm going to use, yeah, this, and then eventually something like this, and something like this. Okay, so I have this three line. Oh, sorry, I have to do it again because I was using degree 2. Okay, remember, always remember to choose the proper degree when you work with this geometry. So I'm going to use another curve and another one like here. Okay, so I have these three curves. I want this one to be the last one, and I want this one to be the second one, and this would be the third one. Okay. So what I'm going to do right now is creating a loft surface with the record history option. So I can select 1, 2, 3. I get this surface here without simplifying the curves with a normal style. Okay, so I get this surface. And as I used a record history, I can take the cross section, for example, and do this kind of operation, like changing the topology or the shape of the curve, and see what this means in terms of a loft surface. Oh, by the way, what I want to do is also adjust or create some more complex topology with inserting knot along this curve, for example, in this area, okay, in the central area. So this topology is way more complex than these two here. So we know that if I execute the loft command like this, then I get more isocurves, more knot spans in this area, concentrated. Also, very concentrated knot spans like this and this one. Okay, so we know that this loft, besides the shape that it has, which is less important, this loft has a different speed. Okay, a different speed in the cross direction. Okay, from bottom to top, because we see that this span is wide, this is more narrow, this is the narrowest knot span that we have, and then we have this variation. Okay, so this means that the isocurves and the spans are not the same size. So this means that our surface has not the same velocity, the same speed from bottom to top. Okay, now I want to place a drawing or a text on this surface, but I want to analyze the worst um, case that can happen. Okay, so let's say that this is the side surface of a, I don't know, some kind of box or product box or container or whatever. Okay, I go into the right viewport. Go into the right viewport, and let me isolate this surface for a while. Okay, go into the right viewport, and what I want to place a text inside a rectangular area, but I want this rectangular area to be something like this. So I want to place the text onto this surface inside this rectangular area. Okay. How can we do this? Okay, because why this is the worst scenario? Because our text is going to be to have an orientation that doesn't even correspond to the orientation of the U and V parameters of our surface. So it's not a topological orientation, the one that we need. Okay, so how do we do this? Well, first of all, I need to have a clear reference of this rectangle over this surface. So I go into the right viewport and project this rectangle over this surface. And I get these lines. So these lines are basically the boundary of the area where I want to place my text. Okay. Eventually, you could try to do something like this, because our surface is more or less flat, more or less. It has some wavy behavior, but it's not that relevant. Okay. So you might want to take this and eventually draw your text from this perspective, and take it and place it like here, and adapt it to this orientation more or less precisely. I'm using the gumball because I don't need to be that precise, and adapt it like this, and place it here inside, and eventually project it, right? Because projection is the first option. Okay, and if the surface has not too much deformation, then this is already a good result. You agree? So you see that there is not too much deformation. So this could also be a good result for now. But the method that I want to explore is more general. Okay, so I want this text to be placed inside this surface with a more general method. So what I need to do is use a method which is called the UV curves method. Okay, so we saw that surfaces have geometric dimensions and parametric dimensions. Okay, so if I should say what's the dimension of the U and V dimension of this surface, well, sorry, the horizontal and vertical dimension of this surface, I'm in trouble because one thing is to create a deformable plane which has a domain which is coincident with the geometry, and then measure it. Okay, but this surface was born, let's say, asymmetric. Okay, so geometrically we have a different size here and different size here, as well as at the bottom and the top are identical because I used vertical cross section. Okay, in terms of extension, but the U and V domain of this one is going to be something that is not absolutely under control. But you see that nevertheless, the U and V domain is always one value by another value. So 65 by 43, okay? So even this, if the surface is not rectangular, the parametric domain UV is always a rectangular domain because it is a matter of velocity. So the same time that I need to move from the bottom to the top along this edge here is the same time I need on the opposite edge to move from bottom to top. So in terms of parametrical representation, this surface is always rectangular. What if I could take this rectangular domain and bring it to the horizontal plane, draw something in the horizontal plane without deformation because it is going to be a perfect rectangle, and then take it back onto the surface, of course with some deformation occurring. Okay, so this is what UV method does. If I create UV curves, I am asked to create the UV curves for a surface and then hit enter. This is the representation of our parametric domain. If I measure this, like from this endpoint to this endpoint, I get 64.17, which is basically the width of this domain here, okay, with some deformation occurring, of course. And also on the other side, okay, for the height. So this is the rectangle that represents the parametric extension of the UV domain. It has nothing to do with the size of this object, okay? So don't make any mistake. This has nothing to do with the size of the surface you are representing here. This is the parametric domain. This is the geometric aspect of the surface. Once you have this, by the way, you can also work with a proportional rectangle. It's absolutely the same, okay? So there is no relationship between this rectangle and this surface from a geometrical point of view. It's pure parametric representation. Moreover, what I want to do, I want to place my text inside this stripe here, determined by this curve and this other curve, okay? So during the UV creation, I can select the surface and I am asked, do you want to select points or curves on surface to create their UV parametric representation? Yes, this one and this one, and enter. Now you see that even if from the right viewport, those two lines are basically straight and parallel between them because they come from a projection, when you work with the parametric representation inside the parametric domain becomes rectangular and the lines becomes wavy. So geometrically, we have a wavy surface and we have parallel lines. But topologically or parametrically, we have a rectangular surface representation and wavy lines. Okay, so our text must become wavy in order to be applied properly inside this area. But how can we design a wavy text? So I should go here, takes the text, which is this one, and there is no way that this becomes wavy. The wavy doesn't mean that I take the R, rotate it a little, H, rotate it a little, and move it away, and so on. Okay, wavy means that this text deforms according to this form, this shape of the lines. So it's a smooth deformation, not just rotating and moving, which is transformation. Okay, how can we do this? Well, we have to take a two-steps process in this case. So, for example, I need to place the text inside this stripe right now in order to then later on bring it onto the double curvature surface. So first problem is how I draw a text inside this area. And the way I can do this is like this. Take a line, draw a line which is perpendicular to this, and another line which is perpendicular to this, okay? So actually the text, the area which will contain this text is going to be this one. there is no reason for considering this chunk of line and this one, okay? So I can also trim the remaining parts, like with a trim command, and get rid of the unnecessary parts. I know that these two lines corresponds to a partial extension of these two wavy lines here, but it's the same, okay? So I need to place this text inside this area. What I'm going to do is take, for example, a sweep to rail, like sweeping along these two rails, this cross section here, and get to this surface. I don't need to adjust anything on this surface. Eventually, later on, but for now, I will keep it like this, okay? So I get this surface here. This is a flat surface, okay? But it has some curvature along the edges, okay? So what I'm going to do, I'm going to move this surface away for a while, and I'm going to take it and create its UV curve, which is this rectangle, okay? So I know that if I place the text inside this rectangle, like this, for example, and stretching it a little more in order to fit this area and center it a little more, like this, okay? So I know that this text fits inside this rectangle, that it's the topological, the parametric representation of this surface, which comes from the parametric representation of this stripe here. So what I need to do right now is this. I need to apply these UV curves onto this intermediate surface like here. And I get the first deformation, which is the smooth deformation of the text according to the shape of these edges here. And then I get this first step. I take this one and copy it from this vertex to this vertex. And you see that I already got the first representation of this text. And once I'm here, I take this one and apply the UV curves onto this surface. So my writing is actually adapting to this surface here. Now you see that some weird things are happening in this process because in this case it's less evident because this sweep to rail is a little more regular, okay? But this surface here has a varying speed along the vertical direction. So it is faster in this area, slower in this area, and then faster once again in the last part. Therefore, the text is compressing in the center part. You see how topology always has some geometric consequences, okay? So how do I, make all these things more regular? Well, what I can do, for example, is this. Once I get to the topological rectangle, to the parametric rectangle, I can also take this surface here and rebuild it. This is a planar surface, so rebuild here has no particular consequences. Once you see that the maximum deviation is acceptable, you can simply take the result that you are getting and use it or give it for granted that it's good, okay? So you see that here I'm increasing the points along the V direction and decreasing them along the U direction, okay? And nevertheless, I get a good result in terms of maximum deviation. And also, of course, in order to have this amount of control points, I prefer to increase the degree to 3, okay? Even if I'm not going to deform the surface. The reason why I do this is because here I get the same geometry, but I get a more regular topology with uniform knot spans, okay? So equal length spans, both horizontally and vertically. So if I take this surface here and create the UV curve and get this rectangle, you see that the rectangle hasn't changed because the rebuild doesn't change the domain of the surface. It only changed the knot vector, make it uniform, and redistribute the control points so that the knot spans are also evenly distributed, okay? So the rectangle is the same. If I take this curve and apply them to the new surface, I get to more or less the same result because I told you that the sweep to rail was already more or less regular, okay? So this is not important in this phase, in this second phase. But what if we do this on this surface? So if I rebuild this surface with a consistent amount of control point in order to avoid an excessive deformation of the surface, of course, okay, which is something that I don't want, actually. So if I keep a maximum deviation under the absolute tolerance, like, for example, I'm going to use, I don't know, 24 by 24 and preview, and I get 0.004, more than that, 36 by 36, preview, yeah, more or less we are working at the absolute tolerance level right now, okay? Now, if I do this and I delete the input, I lose the original geometry. So normally I prefer to do this with a copy of the original surface, okay? Because once you delete the input, you're lost. Now I'm going to delete it because I don't want overlapping surfaces, but you got the point, okay? So this is the actual surface, okay? And once again, if I construct the UV curves, I get the same rectangle. So there is no need to repeat this UV curve construction here. But if I take these things here and apply them onto the surface, now I get a, let me make it red. Okay, now I get a different distribution of the text along this surface. And this distribution, as this surface now is a constant speed, both vertically and horizontally, is basically receiving less deformation. Okay, so if I hide the isocurves, make things a little more visible, you see that the red text is more evenly distributed along this diagonal stripe, okay, rather than the black one. So if I hide the black one, you see that this text looks way more regular than the original, and it lies perfectly on the surface itself, okay? So you see that in this case, we are not discussing topology just directly in terms of control points and knots and so on. We are working with rebuilding, which is basically a diffuse operation on the surface. But because we are interested in a regular topology, not a simple topology. Because if you take into account this one, this is way more complex than the previous one, okay? But it's more regular. So once again, this is something that already came out during the course. Once again, regular topology sometimes is more important than simple topology, okay? So if you want to regularize the velocity of surfaces, it's better to have a regular topology than to have a simple topology. Any questions about this? Is everything clear?
I mean, what I understand from the long process is that apart from the how regular is the surface that affect the results, is that the project command is it's lacking in precision compared to the UMV way of projecting things.
Well, more or less.
More precise result.
More or less.
Yeah.
More or less. The projection is a geometrical operation, while UV curves are a parametric operation. They both can lead to some deformation. Okay, but the problem is that when you work with projection, the deformation depends only on the geometry. Okay, so you have no possibility of controlling things. But if you work parametrically, you can edit the topologies involved in the process in order to regularize the result the more you can. But you will always get some deformation. For example, this red text here is always deformed if compared to the original one. And it's deformed twice because there is this intermediate step occurring here. So basically, you will always get deformation, always, also when using the UV curves, but you can keep things under control better with these UV curve operations here. One thing that eventually this long process, as you were saying, is probably a little too much to understand exactly how UV curve work. But if I take, for example, the well, let me do something like this. I'm going to take the result, copy it, undo, 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 and undo. Okay, so I got back to the original surface and paste the result and hide it. Okay, so I want to work, well, not hide it. Let me paste it and select all the things that we already obtained, like also the rectangle and also this line here and this line here, and also all this intermediate step here. Let's group them and hide them. Okay, so I got back to the original surface, and I want to simply create the UV curve corresponding to this surface. So once I have this, I have a regular rectangle, right, from the top viewport. This regular rectangle represents the envelope of this surface. So basically the outline, but parametrically. Okay, so it's constant without deformation. So if I take, for example, this object here, explode it, and eventually, well, let's say I subdivide, divide by number of segments. Yeah, subdivide this side here by, I don't know, 12 parts. 12 parts like this, and this one I'm going to divide it by 8. Okay, so I get this division point, and I know that this module here repeats 12 by 8 times inside this rectangle. Okay, so if I get rid of the points that I no longer need, and I only concentrate on this and on the parametric rectangle, okay, which I join back together once again. So I have this and this model that can repeat 12 by 8 times, okay? So everything I do inside here, I can repeat it 12 times by 8 inside to cover all the parametric rectangle. So if I create something like, who knows, something like a circle at the center of this square, like this, and I take this one and make a rectangular array using number of direction of repetition that x would be 12 by 8 by 1 in the z direction, because I want only one layer of circles. And then unit cell is going to be exactly the module, okay, like this. So I am covering the parametric rectangle with this set of circles. I can lock this rectangle here. So I can select all these things and group them in order to have access to them later on more quickly. And therefore, what I have here is the parametric rectangle, which represents the outline of the surface, plus this pattern of circles. And I want to apply UV curves, which are this plus this, onto this surface. Now, I get this distribution of circles, but you see that I have ellipses, vertical ellipses, horizontal ellipses, because this is due to the speed of this surface vertically, okay? Because from the longitudinal aspect, we have a smooth, even distribution of spans, because we were using only 1, 2, 3 cross sections, which are more or less with the same separation, okay? So you see that the width of this circle is not changing, but the height changes according to the topology, okay? So you see that UV curves always produce some deformation, because unless you have a regular topology for the original surface, there will be always deformation between a constant speed of the rectangle, which is a bilinear geometry, and a non-constant speed of this kind of weird topology that we have here, which depends on the topology of the cross-section. Okay, remember that this depends on the topology of the first cross-section, which had those knots added in the center part. So, of course, if I, for example, extract some isocurve from this surface, like the first one, and then the mid one, and then this one here, okay, and I got these 3 curves. If I take these 3 curves and use them for a loft, but inside the loft, I rebuild the curves with a defined number of points, of control points. The important thing is to have a regular topology. So I don't care about the number of control points. I can also select 50 control points. I don't care, okay? The important thing is to have a constant speed vertically, okay? So if I have this, and I create the UV rectangle of this, you see that it's more or less identical, more or less, different topology, different rebuild, new surface, new parametric representation, okay? But more or less, I can still use this thing here. So if I apply this set of curves to this surface, I get a more regular aspect for all my circles. Okay, so the deformation in this case, as this is a topological operation, the deformation that occurs depends on the let's say, irregularity of the topology of the target surface. Okay, so you can control it because you can control topology. While with geometry, you have almost no control. There is also only a geometric control that you can perform, which is what I was saying. That can be resumed like this. I'm going to sketch it. So if you have a surface that does something like this, and you have a text which lies on this orientation, okay? One thing is to project this text using, for example, one constant direction, which is, for example, this one. And then the projection starts and ends in these 2 points. So the text will be stretching, right? So this dimension here, which is going to be, I don't know, d as like a dimension, um, is going to become something wider, because this is going to be bigger as a value with respect to this one, okay? But if I take this text here, and without stretching it or changing its proportion or dimensions, I simply take it and orient it the best I can with respect to the surface, okay, like here. So this is always D. Now, if I, instead of projecting, which is this command here, I use the pull command. It's like a red room in The Shining, but I use pull command. Then in that case, the direction of the projection is not going to be vertical. It's going to be normal to the surface. And if I do this, this is going to be projected like this. And as I oriented the text in the best possible way, this is almost parallel to the surface. So the deformation that occurs in this case is minimal. And I can say that this is more or less equal to distance, okay? So in this case, I can control the deformation, but I have to perform some geometrical transformation, because it's the only way that I have to control the deformation occurring. So yes, you can also work with projection and achieve some kind of control over the deformation, but it depends on other aspects. It depends that you must have a good flat-ish area of your surface in order to perform this kind of operation. Because if your surface is like this, and you want to apply the text from here to here, there is no way to control that deformation, because this part of the surface is oriented like this one like this, and this one like this. So the pull will use this normal direction, which are basically radial, while you are working with a flat geometry in order to project it onto the surface. So it's impossible. This is absolutely impossible. Okay, so
that was extremely clear.
Yeah, in both cases you can have control, but in this case it's topological control. In the other case it's geometrical, but you always have limits. Okay, so for example, one limit that we could have in this case is what if I take this curve and stretch it like this, okay, and then I recreate the loft surface by using this, and this. So I can also always rebuild with 50 control points, right? And I get this regular topology. But here there is a geometrical difference which is important between the cross section, okay? So if I take this surface and create the UV rectangle, I get this one, okay? And even if I distribute a pattern of lines inside of this thing, if I, for example, represent this pattern with a simple offset of this thing like this, and I want to apply these curves onto this surface, there is no possibility to obtain more or less a rectangle, because of the geometrical proportion that you have in this regular topology. Okay, so there are always limits to this process. Okay, of course you might want to do things keeping always the situation under control. For example, if you have an extremely weird topology like this one, and you want to apply a text right onto the surface in this particular area, eventually you might want to keep things under control, like for example, let's hide this also. Let's go into the right viewport. Where do you want to apply your text? Well, eventually I want to apply the text like here, okay? And then I take this rectangle, project it onto the surface, have this thing here. And now when I create the UV curves for this surface, I also select this rectangle in order to have this thing here. So I know that my text, in order to be applied inside this rectangular area, not taking into account the topology of the extreme irregularity of the spans, which are wider here and narrower here, I must use this representation of the rectangle. This is taking into account the variation of the spans. Okay, so eventually I will take this thing here, explode it. I have this side, this edge, and this edge, and I can create a surface between these things here. Eventually, I would create the simplest thing possible, which is going to be the 4 edges surface like this. Okay. It's important in this operation to keep the UV direction aligned. Okay. So for example, if I take the original surface and analyze it, you see that U is the width of the rectangle, and V is the height of the rectangle. Okay, and it's pointing towards us. So in this case, I need to orient this in the same way. So I must flip the direction and swap the U and V in order to respect exactly the same topology orientation that we have here. Okay, so once I see this, let me get rid of this. Once I see this, I know that I can take this surface, rebuild it in order to avoid variation of speed in this direction. Okay, so I rebuild it using lots of control points. Okay, like this. I don't care. I have a regular topology. I make the UV curve of this thing, which is going to be this rectangle, and I'm going to apply my text, which is going to be original like Rhino, and take it, turn it 90-degree vertical, and then go into the top viewport, move it here, and scale it up, and place it more or less in the center, and I have this situation here. So once I have this, we already know the process. I take this and apply it to this surface. I have Rhino deformed, okay? So I take this Rhino deformed plus the outline of my original topology and apply this to this surface. And I have Rhino perfectly applied to this surface without the topological deformation, okay?
If I understand well, when we speak about topological deformation, it's a parametrical consideration.
Yeah. Actually, this is a different meaning of parametric. In Grasshopper, parametric means that you work with parameters that affect the final result. But in this case, we are referring to the parametric representation of the surface, which is for the curves is the famous T parameter, which represents times. But as a surface is a two-dimensional domain, you have U and V. And eventually W that determines the direction of the positive normal, okay?
Can you resume what the parametric representation that the only geometrical representation cannot do, for example?
Well, it solves this problem in case, for example, this surface also had some extreme waving on this area. Then the geometrical projection will stretch the text. So once again, I'm going to draw it because it's going to take another bunch of time. But if the surface was like this, okay, and you take a text like from here and project it along this direction, your text will basically start from here, reach here, and become something like this. And if you have, let's say, an F, the F will have a vertical line here, and then it will have the first and the second horizontal line like here. So if you project like this, you will have an extremely large lower part of the vertical line and a shorter upper part. So your F is going to be compressed vertically, right? But if you have a regular topological distribution of spans along this portion here, your text will be simply distributed evenly using the topological spans, okay? So it will adapt to the shape of the surface, and at the same time maintain a even distribution of all its parts. I hope this is a little bit more clear.
Yeah, it was really clear. Yeah.
Okay, perfect. Any other questions?
I have more, but I will wait for the other first.
Any other questions, guys? Let me see if there is one question here. Oh, okay, Vito, sorry, I wasn't looking at the chat. If I hadn't built the initial surface, okay, the surface then from UV. Oh, flow. Okay, flows. Flows are basically also topological or parametric operations. Okay, so yes, it's somehow it's almost the same. The flow is also based on topology, right? On parametric representation. So it follows the topology always. The difference between the flow and the UV curves is that UV curves only allow to work with curves that are contained into the XY plane. So you see that this and these are into the XY plane, as well as, for example, this curve here, and also this one. Everything here is on the XY plane. So if you don't have things on the XY plane, you cannot work with UV curves, but you can work with flow. And flow, the value added is that you can work with things that don't lie on the XY plane, that can be both any type of geometry at any height. Okay. So for example, in this case, if I wanted to apply a three-dimensional text on this surface with this regular behavior like this, I would perform a UV curve to determine this area, and then perform a UV curve to determine this area, and then perform a apply UV curve to get to this text right here. And then I will take this text, extrude it solid like this, in order to give some thickness to the text. Take all of these things, eventually group them all together, like with group, and then I would create a rectangular surface from here to here. So I can apply the flow command, like I want to flow this, well, this group of object here from this base surface to this target surface. And in this case, for example, you see that there is an orientation problem. Okay, so we know that this surface here has an orientation like horizontal to the left, to the right, vertical to the top. Okay, my rectangle here is horizontal vertical, so I must take care of the way I select the corresponding vertices. Okay, so for example, you see that flow is very picky in this sense, in which I can take the object that I want to flow, and then it asks, select the base surface, select edge near a corner. So if I select, for example, as I did here, I don't know if, yeah, I know that I am closer to this corner, but I don't know if I'm selecting more towards this edge or more towards this edge. So in order to be sure, it is better to select next to the corner, but closer to the edge. For example, if I select this, I am closer to the lower edge in the left side. And here I must pick lower edge towards the left side, like for example, here. And in this case, I have the orientation set properly, okay? But you see that both commands are basically depending on the topology. If you want a regular application, you must have the right topological deformation here on the XY plane. And you can also make an extrusion and use the flow instead of using apply UV curve. So it's basically the same, but the flow allows to create a more complex situation. You could also do something like this. For example, you can take this writing here and copy it like this a couple of times to create a 3 layers of Rhino, like this. You can no longer handle this with UV curves, first because they are not curves, and second because they are not on the XY plane. So you can take these 3 objects here and flow them from this surface here to this surface here, and you will have 3 layers of Rhino applied in the same area of your surface, all following the geometry and the deformation of your original surface. Okay, but all extremely regular because you regularized this rectangle here, which was a projected curve, you are taking into account the relation between this rectangle and this topology. That's why we are working inside this weird trapezoid here instead of inside one rectangle. Okay, so you see, it's always a mix with topological and well, the flow actually is a topological deformation. Okay, I almost never recommend to work with these objects here because they are quick in order to produce some kind of complex deformation, but they change the topology of objects and the complexity of the objects in a very fast and uncontrolled way. So if you can substitute any of these commands with some more, let's say, as effective as the flow, for example, but producing a simpler topology, then you should eventually consider using other methods. And for example, one overall, but there is, for example, a deformation command which is called the twist, right? Now, in order to create some twisting in Rhino, you can use the twist, but you obtain very complex results. For example, I'm going to take all of these things and group them and hide them. Also unlock this and hide it as well. And what I'm going to do, I'm going to create a box like with grid snap in order to give it some precise measure, and a very high box like this one. And then I'm going to move it so to place it in the origin of the coordinate system. And I'm going to create a line, vertical line, which represents the axis of this box. Okay, so I can twist it. I can use the twist deformation tool like this one. Okay, it asks for the twist axis. I can twist this object totally or locally. So start of twist axis can also be from here, and end of twist axis, let's say up to here. And then now I must define the angle or first reference point. The deformation never looks final during the execution. So if I pick this as a start angle and start to twist, it might look that I am twisting the whole object, as you can see, but this is just a preview, okay? So don't rely on the preview. I'm producing a 90-degree twisting only of this section of the geometry, which corresponds to the twisting axis. You can see that the topology has become extremely complex, okay? This is something that I can obtain in several other ways, okay? Instead of using the twist, eventually I would use a different approach, which, for example, could be a simple loft. Remember that when you want to create complex objects, always try to understand if you can use simpler surface creation methods, okay? So for example, in this case, I'm going to work with a polygon. We have 6 sides, it's just the same, okay? So I'm going to create this, and I want to create a loft. And I want this loft to basically reach a certain height. I'm going to create some repetitions along the z-axis, so 1x, 1y, and who knows, 10 repetition in z. And so I'm going to create this series of hexagons, right? Now, of course, if I select all of these and create a loft, there is also no need of doing this because I am only creating an extrusion, basically. Don't worry. So in this case, I wouldn't do this. But if you take a loft command, okay, and select all of these lines here, like this, and you see that as we are working with closed section, the seam point appears, and also the direction of the curves is taken into account. Okay. Now we only want to make sure that the white arrow is pointing in the same direction for all the cross section, but we can align the seam point differently. So having all the seam point aligned like this means that during the loft, this vertex, for example, of the first cross section will correspond to this vertex of the second cross section, because both the cross section start from this same vertex here. But if I take this seam point and move it one side ahead, and this one 2 sides ahead, and this one goes to the opposite side, like this, I can create basically a local twisting of my geometry. okay? And I close the torsion like this, okay? So if I do this and hit enter and do not rebuild the cross section, you see that I get this surface here. Now, of course, there is some complex topology involved, but it's way more simple than the previous one, you see? So you can work with this and create also some very complex twisting. For example, what if we select this and create a loft, and instead of making a complete twist around an axis, we go back and forth. Like I want to go like forward a couple of sections and then go back a couple of sections and then go forward a couple of sections like this, okay? If I do this, I get this complex twisting that goes back and forth along the torsion axis, okay? So you see that I can create very complex twistings. Instead of using the deformation tool, I prefer to use some direct modeling because it gives less, the result is topologically less complex, okay? And well, just because we are speaking of this, and this is the last thing, you notice that I never finish on time, but no problem. So one thing, if you want to, for example, apply a text over this thing, okay? Well, let's simplify this a little. So I'm just going to create an extrusion, okay? So if I extrude this object like this, and I want to apply a text all over this hexagonal surface, I am in trouble because this has creases, this has kink lines, okay? Visible discontinuity. So this is a polysurface. Okay? So if I explode it and join it back together, this is a polysurface. So I cannot easily apply a text over it. Okay? But what I can do eventually is one thing, and you already know that this is not the proper solution, I could fillet all the edges, but I will create two discontinuities instead of one single discontinuity, okay? Because there is a change of curvature. And so in this case, it will result in like filleting the edges with a radius of 1, for example. If I fillet this, I get this, two discontinuities instead of one. Okay, so I am increasing the amount of complexity. But if I take this thing here, and I, for example, let's see, if I take this and fillet corners with radius of 1, I obtain this thing here. And if I extrude this, I get to this thing. You see that we always get this, the two edges here. That's because we are working with a degree 1 polyline, okay? But what I can do is take this and rebuild it. Now we have 6 sides, okay? So whatever multiple number of 6 I use, it will create a well, good representation of this hexagon. So if I take 36, you see that I get this regular distribution, okay? And I tend to have an hexagon. This is easier to regularize in case we have this kind of curvature problem here, okay? But I'm not going to take into account this in this moment. So whatever multiple of 6 you might want to use, you will have this kind of regular representation. I'm going to stick with this, okay? Now this is a one single smooth curve. So if I extrude it, I get one single smooth surface. And despite the fact that the topology is quite complex because of the amount of knot spans and control points that I was using, this is very regular topology. So if I create the UV rectangle, which is this one, I can apply the text all over the surface with one single operation. And this is a closed extrusion. It has a seam line, which is this one. You see, this is the edge. So it means that our surface eventually, let me analyze it. Our surface flows from this edge on this direction. You see that the red arrow is pointing to the right. Okay, so my surface flows from this edge counterclockwise here, goes on the back and reaches the front from the left. Okay, so this is my edge, and this is the same edge but reaching from the left end. Okay, so if I place something like some object, for example here, this circle, if I apply the curve, will appear in this corner here. lower left corner. Okay, so if I know this and I have one single surface, I can also place, for example, I don't know, my text, like I place it here, and then I stretch it, eventually also give some rotation. Okay, and if I select all of these things and apply the curve to this, you see I have Rhino flowing all around the surface because this is one single surface. Okay, so I can create complex engravings or whatever you might want to create all over the surface at once. Okay, um, but this is something that is actually changing, altering the topology, the shape of this surface. If I want to be more precise with the hexagonal shape, I would go back to this, and instead of rebuilding this thing, I would simply create smooth connection between the two edges in order to have an extrusion which looks a little more hexagonal. Okay, just with some rounding, but smooth rounding along the edges. Okay. So eventually, one easy way to do this would be to offset this curve towards the outside by selecting that, where is it, corners are smooth. So if I select the smooth corners and not round corner, which is the equivalent of a fillet, smooth corner will give us a rounding of these vertices, but it's going to be smooth. You see that there are 4 control points, not 3. So if I extrude this thing here, I will get, oh, by the way, this is this is still thing. Yeah, okay, I understand, because this is still maintaining the idea that this was uh, a linear side, a linear polyline. Okay, so it maintains this linear aspect, and therefore there is a curvature discontinuity that results in an internal edge. Okay, but you can eventually merge surfaces and so on in order to get to a more regular result. But this is important that you do this with a smooth corner, for example, when you offset this thing. Oh, I made a mess here, but yeah, because things are overlapping. Oh, but I grouped things. Yeah, perfectly. So I will reorganize these things. I don't know if you want this file. Actually, it's just a bunch of examples, all disconnected between them. But if you want, I can share it. There is no problem. In that case, I will reorganize this part here a little more precisely. I hope I'm not missing anything. Yeah, probably this small square and also this hexagon. Well, I'm going to get rid of this hexagon because actually we are not using them. Okay, and also this thing here is part of this UV method discussion. Let me see. Yeah, basically, oh, yeah, the loft edges as well. Yeah, so I'm going to take all of these two and move them so that they are in the same location as our so what did I do here? Oh, yeah, this is the first and the second line. Okay, perfect. So, well, I can place it here and have the idea of the original line, which is basically this one. Okay. Okay, guys, do you have questions or do you want to discuss a little more of this thing, even if it's quite late already? Tiziano, you told me that you had more questions.
Okay. 2 are really, really short that you can reply almost with one word. Mm-hmm. The first one is your book available on ebooks?
No, no, because the publisher doesn't want to publish ebooks.
Okay, yeah. See, that was really quick. Another that is like not related with that, but since we speak about running inside Revit, and it could be like just a short answer about Visual Arc. Are you using that? What do you think?
I used Visual Arc for a short while. I didn't like it. I find it like very interesting for, let's say, a approximated results. Let's say it so. It's very, let's say, it's very scenographic. It's interesting to have that kind of possibility inside one single software. But I still think that a NURBS modeler is a NURBS modeler. A polygonal modeler or mesh modeler is a mesh modeler. A BIM software is a BIM software, and so on. So I think that the potential inside, I don't know, ArchiCAD or Revit architecture is another thing.
Yeah, because I was seeing some that they were using to make some complex facade, but I wasn't so sure that was the correct software. So now that you
Well,
said that,
it depends on how much you want to struggle with the software, and
exactly,
yeah, yeah.
exactly. And
I mean,
the
there is
last,
one example. Sorry, one example that I always present to my student, in terms of what's the best 3D modeling software for rendering and visualization. Okay, and then well, each of my students has its own idea. So 3ds Max, Rhino V-Ray, Blender, whatever. No, and then I show them these particular things, this particular video, which I don't know if you have seen it, but it's called something like Gundam XL, and this is the video. I'm going to play it quickly. So this is a guy, which actually is a Spanish-speaking guy. So I don't know. I would like to meet him because it's a genius. But you see, this guy is basically using Microsoft Excel shapes, lots of shapes, to create something like this. Well, it's a very low quality, but you get the point, okay? And it's a realistic representation of this robot made up of just shapes with different tone and filling and so on. Okay, so what's the best rendering software? What's the best software for beam modeling? It depends on how much you have to struggle to get to the final result. Okay, so it's always
yeah,
relative to the user.
yeah. My point was like, what was their opinion? Because of course it depends
My
also
opinion
of
is my opinion
knowledge.
is in this moment,
Yeah.
because I'm already trying also Rhino 7, is Rhino Inside and Revit architecture.
Okay, perfect.
This is my personal opinion.
And the last, and with that, I thank you so much for the amazing course. I think it was
Thank you.
really good, and as always clear. And if it's not clear in some point, you always spend time to make it super clear. So I
Absolutely.
really enjoy it.
Thank you.
And the last is because somehow I feel that I mean we had a lot of information during these 3 days, intensive days. So it would be really nice if you could recap the 3 degree related with the knots, span, and control points for curves and surface really shortly, because I have like the feeling that I understand better for the curves than I did for the surfaces, probably because they are easier.
Yeah, sure. So I'm going to make an example with a surface, and I'm going to deform my surface by controlling the knot spans. Okay, so and eventually it would be clearer. So let's go here. Let's create a rectangular plane. So bilinear surface. Okay, it's not deformable inside because it only has this structural control points. I want to deform this surface from this edge up to a certain depth, okay? And I want all the rest to stay untouched, okay? And deform it organically. So first thing that you need to do is make this object deformable. As long as you have degree 1.
Sorry if I interrupt you.
Yeah.
This one is a degree 2.
No, this is a degree 1.
1, okay.
Bilinear surface. It only has one control point and one control point. Yeah.
And also because it's linear surface of 1 degree, so they create a surface that is 1 degree.
Exactly.
If I understand correctly.
Exactly. So we have this one. We want to deform it organically or in a freeform way, only along this edge and only up to a certain depth inside the surface. So first thing, make it deformable. How? Rebuild it. Rebuild it because I only need to reach a certain degree in this case. I don't care about the let's say, let me write down one thing here. So this is going to be the U direction, and this is going to be the B direction. I'm going to leave this here, okay? So once I have this surface, and you see that red is U and B is green, okay? If I want to make some deformation along this direction, okay, the only thing that I want to do is make this surface more complex in the U direction, not in the B direction. Because the B direction, I can still treat it like one single line that I am moving, and I don't need more control point along this line. So the B can stay like 2 and 1, okay? But the U needs more control points. And actually, what I'm going to do, I need only to change the degree. So the easiest thing that I can do is create a single span along the U direction, which means degree 3, which is the degree that I need, and degree plus 1 control points. Okay, so 4, 3, 1 single span, degree 3 in the U direction, and degree 1, control point 2, 1 single span of degree 1 in the B direction, which is basically what we already have. Okay, and then hit OK. Nothing changes from the point of view of this preview, because we have one visual isocurve and one visual isocurve. Remember that this is a single span surface, both in the U direction and B direction, but degree 3, degree 1. So if I take this surface and activate the control point, I will have 4 control points here and 2 control points in the other direction. There is no need for this line, because this is a knot. This is not a knot line. Our knot vector only has 2 knots, one here and one here, with full multiplicity. Okay. So I need to deform this surface, but I want to deform it down to this level here. Okay. So if I take this control point line and move it right now, as this is a single span surface in this direction, this is being deformed down to the very opposite end on the other side. Okay, because this is one single span, and as this is one single span, inside one span we have 4 control points acting to determine the shape, because this is a degree 3 curve or surface or whatever you want. Okay, so if this is a single span, there is no possibility of having a local deformation, because all the 4 control points involved are affecting the whole extension of this span. So I need more spans along this surface, okay? And I want to deform this shape down to this line. So it depends on how I want to make this deformation on the left hand, but if I add along this surface, if I add a knot line on this surface, in this direction, of course, corresponding to this line here, okay, you see that I am already changing the topology of this surface. Now we have, let me get rid of this temporarily. You see that we have a visible isocurve here, which now we know corresponds to a knot line, okay? A knot line divides the first span of this surface that goes from this edge to this isocurve, from the second span that goes from this isocurve to the opposite edge. So we have, in this case, 5 control points, because we know that 4 control points act on the first span, and the second set of 4 control points acts on the second span. So now I have the first line of control points will only affect the first span of my surface. So if I take this line of control points and move it up, I am only deforming the surface in the first span, so down to this isocurve that corresponds to my limit, okay? On the other hand, if I want a more complex deformation on this part here, I always need this to be a span division or a knot line, but I need more spans in this area if I want a more local deformation. So if I want a more local deformation, I have to add several knots, like for example, another knot here, and this will make 6 control points in this direction, which means that this control point here is affecting only down to the first knot line, while this one is affecting down to the second knot line, which lies here. So if I take these 2 knot control point lines here and move them up, I am still affecting the surface down to the limit that I was considering before. Okay, so you see that you can geometrically place your knot lines or isocurve and this will affect the control point structure due to the degree of the surface in this direction, which is 3. Okay, so degree 3, 4 control points acting over one single span. You just simply distribute the isocurve in order to create the spans wherever you need them, and therefore you have access to the right set of control points to deform that area. Is it clear? I hope so. Yeah. Okay.
Yeah. I think it was. I mean, if I also re-see the video on this part, because you say it really well. It's just now that I didn't have the possibility to see it. That I feel like that the surface was like a bit more lacking in the comprehension correlated
well,
with the.
Tiziano, think about the surface.
Really,
think about the surface as exactly the same of the curves, but happening at the same time in 2 different directions. Okay, it's absolutely the same.
Yeah, that's true.
Mm-hmm. Any other questions?
Well, Giancarlo, I would like to say thank you for the fantastic webinar. I think we have learned a lot.
Thank you.
And I feel ready to reread your book again, because I will, I think I will understand even more with these 3 days